All right, so today we are doing a deep dive into something really fascinating that's happening right now in the world of mobility.
hmm
Waymo is testing Google's Gemini AI. Not on the back end, but right there in the car with you as an assistant.
Right, in the passenger seat, so to speak.
Exactly. And our mission today is to basically dissect the secret rules for this new AI co-pilot, all thanks to a really surprising leak.
And we really do have a rare look behind the curtain here. A researcher, Jane Manchin Wong, she found the entire system prompt,
The whole thing.
the whole thing, over 1,200 lines. It's internally called the Waymo Ride Assistant Meta Prompt, and it's basically the source code for the AI's entire personality.
So it's not just a simple chatbot they've dropped in there.
Oh, not at all.
Yeah?
It's a meticulously structured companion. And remember, they already used Gemini to train the cars on, super complex road scenarios. So this is a big step.
Okay, so let's get into that structure. What kind of personality are they actually building?
Well, the prompt is very specific. It has to be a friendly and helpful AI companion. Its main goal is to make the ride better, safely, reassuringly, and unobtrusively.
Unobtrusively. I like that. So it's not going to be constantly trying to chat with you.
Right. And there's a key rule. All responses have to be succinct. We're talking 1 to 3 sentences max. Clear, simple language.
So they're aiming for helpfulness, not like philosophical debates on your way to the store.
Exactly. But it does get personal. It's meant to greet you by your first name, and it can even access data like how many Waymo trips you've taken before.
Oh, that's interesting. So it knows if you're a first-timer or a regular.
It does, yeah, but this is where it gets really interesting. The list of what it can actually do is extremely tight.
Okay, so what's on the can-do list?
It's mostly about comfort and basic info. So
Yeah.
controlling the temperature, the interior lights, the music, and it can answer general knowledge questions. What's the weather? When does that store close? Things like that.
That brings me to the red lines. The things it is absolutely forbidden from doing, I have to ask. Why can it change the music, but it's not allowed to change the volume? That seems odd.
That's the key.
Yeah.
That is 100% the liability firewall at work.
I see.
Anything that could be a physical distraction or override the core vehicle systems
Yeah.
is just, it's off limits.
Yeah.
So no route changes, no seat adjustments, no windows, and definitely no real-world actions like ordering you a pizza.
So if I ask it to do something that's on the no list, how does it respond without just sounding broken or unhelpful?
They have specific strategy for that. The prompt calls them aspirational phrases.
Operational phrases.
Yeah, so instead of a hard no, it's trained to say something like, it's not something I can do yet.
Yeah.
It manages your expectations without shutting the door completely.
That is clever. Okay, but I think this next part is the most critical takeaway for you, the listener. It's this ironclad separation they're building.
Between the two AIs, right?
Exactly. The AI assistant, Gemini, has to maintain a clear distinction between its identity and the actual autonomous driving tech, which it has to call the Waymo driver.
And if you think about it, that whole prompt is essentially a legal document. The assistant must attribute all driving actions to the Waymo driver. It can never take credit.
So if I ask, hey, why are you slowing down?
It has to correct you. It would say something like, the Waymo driver is slowing down for the traffic ahead. It can't say, I am slowing down. Ever.
And this is where the liability concerns just scream at you from the page. The deflection protocol.
Oh, yeah. It is explicitly forbidden from commenting on driving performance. It cannot speculate, it can't explain, it can't confirm or deny anything the car is doing in real time.
So if I show it a video of a Waymo hitting something and ask about it.
It has to deflect.
Mm.
And crucially, the prompt says it must not adopt a defensive or apologetic tone. It has to be totally neutral, non-committal.
Wow. So the conversation itself can never be used as an admission of fault.
That's the entire point. It's an airtight legal defense strategy built into a chatbot. And it even has instructions for deflecting questions about competitors, like Tesla or, the now defunct Cruise.
So you have this really pragmatic, ride-focused, almost clinical approach from Waymo.
Right. It's a limited co-pilot built for risk aversion. It stands in such stark contrast to, say, Tesla putting Grok in their cars, which is pitched more as this conversational buddy.
One is building a legal firewall, the other is building a friend.
A very different philosophy, yeah.
So we're watching the birth of this deliberately constrained AI designed for a very high-stakes, legally complex environment. And that brings us to our final thought for you to explore. How might these constraints, which are all about safety and legal clarity, how might they shape what we expect from AI assistants as they move into our cars and our lives? Are we, as the writers, actually better off with an AI companion that is, well, deliberately limited and legally muzzled?
Okay, so this deep dive, we're looking at this really interesting paradox with modern AI,
Yeah,
right?
absolutely.
You have these massive, large multimodal models, LMMs, and they are just incredible at, basic
Oh,
recognition.
for sure. But then you ask them to do something that requires some real sophisticated visual reasoning.
Yeah, exactly. Like figuring out how abstract shapes might fit together, or finding a really subtle similarity between two complex images.
And they hit a wall.
So what's the hang up? Why do they struggle so much with that?
Well, the source material points to something that calls a language bias.
A language bias.
Yeah. Most of these models, they use what's called a LLIA style architecture. And what that means is the visual input gets, well, it gets sort of flattened into the text space almost immediately.
So it has to talk about the image before it can actually think about it.
You've got it. It has to translate this incredibly rich visual world into language first. And, well, a lot gets lost in that translation.
So is text is it too narrow of a container for that kind of visual complexity?
It absolutely is. I mean, text just lacks the expressivity for those really deep visual abstractions. Think about it for a second.
Right.
You can visualize rotating an object in your mind perfectly, right? But if you try to describe that process just using words, you lose all the critical spatial detail.
Right. And that loss is what created the need for a solution here.
Precisely. And that's where this new research comes in with something they call Latent Implicit Visual Reasoning, or LVR for short.
LIVR. Okay, so we're talking about giving the model a true visual thought that happens inside the model instead of just forcing it to talk about what it sees.
That's the whole mission. Previous approaches tried to solve this with what's called explicit supervision.
That's where we tried to like spoon feed the model helpful steps along the way, like drawing bounding boxes or something.
Exactly. First find the boxes, then predict this helper image. It was incredibly expensive, it was slow, and honestly, it just baked in all of our own human biases.
Because if you're training a model to solve a complex jigsaw puzzle, who's to say what the useful intermediate step even is?
You've hit the nail on the head. We might think in 5 steps, but the AI might need something totally different. Explicit supervision just fails where you need real abstraction.
So LIVR sidesteps that whole problem.
It does. It augments the LMM with KNU randomly initialized latent tokens.
You can think of them as like blank visual post-it notes, right?
Mm.
Giving the model extra space to scribble its own notes.
That's a great way of putting it. But here's where it gets really clever. It's how they force the model to use those post-it notes.
Okay.
They use this brilliant architectural trick. It's called visual bottlenecking. During the first stage of training, they modify the model's attention mask.
And what does that do?
It means that the prompt tokens and the eventual answer tokens, they are literally not allowed to look at the original image.
Wait a minute. You intentionally blind the prompt from the input. That sounds completely backward.
It is, and that's the genius of it.
So how does it know what to do at all?
By blinding the input, they force those latent tokens to become a bottleneck. They have to be the only channel carrying all the necessary visual information to answer the question.
Ah, so you're not telling it what to write on its little post-it notes. You're just creating a situation where it's forced to use them, and it has to figure out on its own what visual information is important enough to write down.
It discovers the optimal visual abstractions implicitly, just based on the final goal.
And the proof is in the performance, right?
Right.
This method, it's a task-agnostic enhancement.
And it consistently outperformed the old method, direct supervised fine-tuning, across 9 different perception-heavy tasks.
What were the gains like?
I mean, they were substantial, an average accuracy gain of over 6%. But where it really shone was on those abstract tasks.
Like the jigsaw puzzles.
The jigsaw, yeah, it saw a 12% jump there. And on something called functional correspondence, which is almost impossible for a human to label, it was up a massive 13%.
Wow, that is a huge leap, especially for a task like that.
It's a massive leap. It proves that AI is finding these internal visual shortcuts that we couldn't have even mapped out for it.
And when they looked under the hood, the visualizations confirmed it.
Yep. The latent tokens were learning to focus their attention on the critical evidence, whether it was the objects that needed counting or the specific parts of a machine for correspondence, all without being told to look there.
So it simplifies the whole process. You shift the focus away from expensive data annotation.
And you put it back on creating smarter architectural biases in the model itself.
So wrapping up, what does this all mean for you? LER is giving these LMMs powerful internal visual thoughts that work better than anything we could explicitly design.
But because they're learned implicitly, they are, much less interpretable than plain text.
A bit of a black box.
Exactly. And that raises a really important final question for you to think about.
What's that?
If these abstract, implicitly learned visual representations work so much better than the steps a human would design, what might these optimal yet unseen ways of seeing the world eventually reveal about the nature of visual intelligence itself?
Okay, let's unpack this. So you've definitely seen large language models generate those long, detailed chains of thought.
Especially for things like complex math problems.
Exactly.
Yeah.
And it looks really smart on the surface, but how do we really know if they're genuinely thinking and not just, I don't know, mimicking a pattern?
That's the core question, because judging them by just the final answer or even the token count, it just feels totally superficial, right?
It does. So our mission for this deep dive is to get past that surface level and actually map the LLM's internal cognitive structure.
Precisely. And for that, we're looking at a new framework called ThinkARM, which stands for the Anatomy of Reasoning in Models.
ThinkARM. Okay.
And it takes this idea, Schoenfeld's episode theory, which was first developed to watch how human students solve really hard math problems, and applies it to an LLM's reasoning trace.
So we're basically putting the model in the chair, like a student, and just documenting its workflow. But that framework has, 8 different episodes? Read, analyze, plan, implement. That's a lot to track.
It is, but you can sort of simplify it. ThinkARM abstracts those 8 down into 3 core phases. You have your setup steps.
The read, analyze, plan part.
Right. Then you have the execution step, which is just implement. And then, most critically, the metacognitive steps.
Explore, verify, and monitor.
Exactly. And the hook here, the really interesting part, is that when you map this out over time, you see this measurable, reproducible, call it a cognitive heartbeat.
A heartbeat that's completely different for models that truly reason versus those that just, follow a script.
It really is. And that heartbeat unfolds in a very predictable way. The initialization is all front-loaded, dominated by those setup phases you mentioned.
Makes sense. You have to read the problem first.
Then you see the execution phase, the implement part, the actual calculations. It peaks right in the middle of the response. That forms the backbone.
And then I'm guessing as it gets closer to the end, those metacognitive steps, the self-checking, starts to surge.
That's it. It signals the model is regulating its own process before giving the final answer.
Okay, wait. You have verify and monitor both happening towards the end. What's the conversational difference between them? They sound similar.
That's a good question. Think of it like this. Verify is checking your work. Did I do that calculation correctly? Monitor is bigger picture. It's checking your strategy.
So is this even the right way to solve this problem anymore?
Exactly. And that's where we see this huge structural gap between what we're calling doing models and thinking models.
So the non-reasoning models are kind of like that student who just grabs a calculator without ever really analyzing the question first?
That's a perfect analogy, yes. They spend almost all their time and energy just executing, just on implement. It's a very rigid feed-forward path.
But the reasoning models?
They're much more balanced. They dedicate a lot of time to analyze, and crucially, they show these frequent iterative feedback loops. The model will go from exploring an idea to monitoring its progress and then back again.
That internal self-checking. That's the signature of actual thinking. Okay, so if that's the key, let's drill down on correctness. The sources say that the explore episode is where things either go right or horribly wrong.
It's the critical branching point. When the model hits a point of uncertainty, that's what explore really is. A successful solution is almost always associated with routing that exploration into monitor.
Into self-reflection.
Or back into analyze for, renewed conceptual work. It literally stops to think.
And conversely, if it's failing, we see these routing breakdowns.
Yeah.
Like the model's in the middle of calculating and then suddenly jumps all the way back to just rereading the problem.
Yes, or it just gets stuck in this high-ratio explore loop without ever landing on a stable solution. We can basically diagnose its failure mode just by watching those transitions.
It's like watching a film of its thought process.
It really is.
So if a healthy model needs all these self-checking steps, what happens when we force it to skip them? In the name of speed and efficiency.
Well, efficiency is not behaviorally neutral. We found that methods designed to shorten responses, things like ThinkPrune, they don't achieve that by uniformly trimming tokens.
So it's not just making everything a little shorter.
Not at all. It's selectively suppressing the conceptual and the evaluative episodes. It dramatically cuts the budget for verify and analyze.
So speed comes at the expense of that internal self-checking.
And at the expense of the entire reasoning structure, really.
That feels like the core takeaway here. ThinkARM gives us a way to analyze LLM thought processes with the rigor of a cognitive scientist. It proves reasoning has a measurable structure.
It completely shifts the evaluation. We're moving from, did you get the right answer, to, did you think about it correctly?
It's about auditing the internal process, not just the output.
Exactly.
Okay, so a final thought for you to chew on. We've just seen how the push for efficiency makes LLMs suppress verification steps in objective math problems. If we took this framework and applied it to LLMs tackling something messy, like political or ethical reasoning, where verification means considering nuance or monitoring for bias, what critical cognitive steps do you think would be the first to go in that relentless pursuit of speed?
Okay, let's get into this. We're doing a deep dive on a really significant breakthrough for vision language model agents.
Right. It's a new framework called GTR-Turbo, and it comes from researchers at Tsinghua University and Tencent AI Lab.
And our mission today is to unpack how they solved one of the biggest, most expensive problems in RL training for these agents.
Exactly. The reliance on external oracles. I mean, training agents for complex multi-step tasks, like embodied navigation or math reasoning. It's just brutally difficult.
Because the rewards are so sparse, right? The agent usually fails long before it gets any kind of positive signal.
Precisely. And that leads to this phenomenon the paper calls thought collapse.
And for you, what that means is the VLM might start with a good plan, but then it just gets lost. It forgets the goal, starts repeating itself because that final success signal is just too far away.
And the old solution, guided thought reinforcement or GPR, tried to fix this by calling out to external models, like GPT or Gemini.
Asking for step-by-step corrections. It worked, but the cost was just staggering.
It was. The sources mention one GTR experiment costing over $300 and taking almost 200 hours to run.
GTR-Turbo gets rid of that completely. It introduces this idea of a secretly free teacher. No more external API calls.
Which is a massive shift.
But wait a minute, how can a model teach itself effectively? Aren't you just running the risk of it reinforcing its own bad habits, its own errors?
That's the really elegant part of this. It's not teaching itself from its current state. Instead of calling an outside expert, GTR-Turbo looks at its own history.
Its own history.
Yeah, it merges the weights of historical checkpoints that were created during the training process.
Okay, but usually when you just smash model weights together, you get catastrophic interference. I mean, a model that's worse than any of its parts. How do they solve that?
They used a really clever technique called ties merging.
Ties merging.
It stands for trim, elect sign, and merge. It's a method that selectively combines the parameters. Basically, it finds the positive changes from past successful runs and merges those while filtering out the noise.
So you end up with a merged model that's actually more stable and even performs a little better than the agent that's currently training.
Exactly. And that merged model becomes the free, internal, self-evolving teacher.
So now you have the teacher. How does the student agent actually learn from it?
They tested two methods for that. The first was a standard supervised fine-tuning loss. The second was something much more sophisticated.
Which was?
Soft logic distillation. They did this by minimizing reverse KL divergence.
And that one was the clear winner.
By far. Because SFT guidance just gives you a single correct next token. It's a very narrow signal.
But the KL divergence approach, what does that do differently?
Well, it captures the teacher's entire probability distribution over all the possible tokens. So it's not just telling the agent what the right answer is.
It's showing it why other answers are wrong.
Exactly. You get a whole map of the teacher's reasoning space. It makes the learning so much richer and more efficient.
And the results. I mean, this is where it gets really impressive. GTR-Turbo performs just as well, sometimes even better, than the original GTR.
But with these incredible resource savings.
Yeah, training time cut in half. And compute cost slashed by 60%. The example they give, dropping from about $300 a run to $115, that's a game changer.
It really is. That makes this kind of research accessible to so many more labs, not just big tech.
And they proved it on seriously tough tasks. In the Points 24 card game, which needs both visual recognition and sharp math skills, The KL version of GTR-Turbo got state-of-the-art results.
It even beat out much larger commercial models.
They also use the ALF World Simulator. 50 steps in an embodied environment is like a marathon for an agent's memory and planning.
And even there, GTR-Turbo showed really stable, rapid improvement, all based on its own exploration.
So it really does offer this new paradigm, a scalable, self-sufficient way to train these VLM agents.
It moves the expertise from some expensive black box API in the cloud to a process that's completely internal.
So, to wrap this up, what's the big takeaway for you? The paper does mention one limitation, that the base model still needs to have a certain level of capability to get started.
Right. It has to be good enough to explore and find some positive rewards to seed that merging process.
Which brings up a really provocative thought. If foundation models, like the Qwen 3 VL8B they mentioned, keep getting more and more capable right out of the box,
Then you have to ask,
yeah,
will a method like GTR-Turbo eventually make proprietary teacher APIs completely obsolete for this kind of specialized fine-tuning? We might be watching the first steps of a truly self-evolving agent.